We're working. Yes, I'm recording now. Camera, but I can't scale the camera. Anyway, guys, this is Entropy stuck in Merlin's lattice. Guys, this is very important to understand. This is very important to understand. It's got OBINexus partial derivatives. Let me start introducing myself. I'm Namdi Makeup. I'm the fan of OBINexus. This is about partial derivatives, but it's like in the dimensions above us. Things that we can't observe interact with in our dimension, 3D. With 4D lattice we're talking about, but it's really lattice geometry lattice in our dimensions to the world. So let's get started. But I'm gonna give you the legend. I've got a paper here, but I have to try to give you an example. Try to upload the picture of this to my phone and then try to put it on my post. But I'm modeling the same thing here. Just make sure that you're following on the screen. Okay. So, hidden axis metaphor. The hidden axis metaphor and the geometric bounds, the model ingredient, the residue entropy formula, and the OBINexus audit trail. The take home message. Okay, let's go. Hidden axis metaphor. Okay, a hidden axis presents true ground state element. So basically, if you remember Merlin, Merlin was like a movie, a show. But Arthur couldn't pick up the sword. Merlin could pick up the sword. But if it's in 4 dimension, Merlin cannot wield the sword. So no one can wield the sword if it's really magical, because the Merlin cannot ever pick up the sword. Whether it's just 3D, this magic is by 3D construct in the world. If it's 3D, it stays in 3D. You have to get for the Merlin to ever live this kind of sword. It's stuck forever because the lattice is in 4D, 4 dimensions. Continue. The ridge retrieves minimum energy, but not a unique state. Cooling only rotates the handle. So basically, 3D operators cannot access the log tilt axis. The log tilt as the 4 dimension, because axis bound by 3D cannot use 4 dimensional properties to the full extent. You cannot get a 3D and project yourself forward into a 4D state. You cannot get an energy. Basically, you have to get an energy to get an energy from a 4D. To use the property of a 4D, you have to be in the 4D world. Basically, it's like an ant. Being in 2D world cannot being in 2D. You cannot use the property. You cannot extend your hand to 3D because you are bound by 2D rules. Same thing here with the 4D people. Next, 4D force prediction. Move the axis. This is just basically it's on thermodynamics. Thermodynamics rule 1. The first rule of thermodynamics. Basically, rule 3 that never applies. This I'm trying to prove. The third rule of thermodynamics is the system decoheres itself because have infinite energy. Basically, I'm trying to say prove to you the third rule of thermodynamics apply to anything in the world. It never applied. It never will apply. Because it's just about you can never the perpetual memory motion device, which is a wrong interpretation of the system. If you put it into the system can continue indefinitely, but system doesn't need to stop because friction is not a force. It slows it down, but it doesn't apply to Dari in this context because friction slows it down. But the perpetual motion rule doesn't work because our construction doesn't work. We don't understand how it doesn't work, which I'll give you now. So basically, the figures here are quite long. So let me just try to give you guys in the way I understand it, in a good way, so you can all understand it. 4D force, the movable axis. So basically, I'm gonna start with basically 3D observable force is bound by the experience of this experienced by the experimenter. Therefore, the force in 3D is bound by the 4D construct of the substrate of the 4D construct Fx, Fy, and F2. The F where the component is lost, making the element impossible. Basically, you cannot project yourself. You can use the force. Basically, a 3D force, not a 4D force, in the full sense. Therefore, if you have like a property Fx, Y, and Z, you lose the width dimension entirely because the width dimension it comes to time. You don't feel the time pass. You basically the time is no effect principle in this dimension. I can conceptualize the time. I can know what I'm doing in a time, but I can't take a full measurement of that dimension of time in the most precise form. If this time, that's the 4 dimension above us, because that 4 dimension of time has been sparsely projected into our reality, but we can only measure time relative to something else. If it was in 4 dimension, I can go back in time, but I cannot go back in time if I wanted to with a time machine. that could be one dimension. It could be like I cannot go past the boundary of the x component, because I can't go up, side, side, side. I cannot walk all the way around the Earth because some kind of boundary or just an axis in the universe, observer universe, take a measure of some kind of direction. Because the sparse modeling shows that we resolve the dimension in 3D. But I cannot iterate the 4 dimension in the full extent. Some kind of like piecewise elimination. Basically, the functions stop being continuous. It's like a peak point. So basically, it's the you can't. It's a cutoff point between you have to measure. You have to resolve it. Like you have to change how you measure that change before the Franklin function cuts out. So that's what I'm talking about the system. So if you have like a function, example, even give an easy one because I don't want to bring guys bang. If x is modulo 2 is even, if modulo 2 equals 0, 0 print even output even. Else if x modulo 2 equals 1, print odd. This is just one example. This is like a Franklin function. This is like if x is less than or greater than 0. Usually this is even. Output 1, 0, 1. But the boundary of even one is not like the main boundary concern. It's more about ensuring the system doesn't break its trajectory when it sees like an input that's -1. Because -1 modulo 0 is a negative number that will give you things of different properties. Like a negative number is -2, it's even. But -2 is not a positive number, it's unsigned int, it's signed int. It's a sign on 0 to 2 divided by modulo 2 modulo 2 2 divided by 2 is 1, so you get -1. But it's -1 even and odd. 2 divided by 2 is 1. -1 is that's odd. It's odd. So this kind of odd number, it's wait, if 2 divided by modulo 2 is 1. But 2 divided by 2 is 1. But 1 remainder, 0 is 0. So this is an odd number. So some kind of thing doesn't really align with it, because you have to cut off to ensure that it continues somewhere else, or sometimes it doesn't. That's why it's franking, because franking can be continuous function. We can trace for calculate, show no derivative loss. But if you have some kind of, let's have kind of resolve that state based on a modeling of the piecewise strategy, we can ensure the thing works. An example I'll give you is like the quantum one, because this is more interesting to what I'm saying. So I think that symbol is gamma. That little symbol, I can't remember what it's called, but look like a table. Okay, I think let's call it gamma. So gamma 3 projects, especially to project your force. The force of a 3D object is versus gamma 3 from the force of 4 to x where the components are sparse. Now the f is completely lost, because you project downwards. For example, the 4D vector is quasi. Quasi means it's the quasi means the quantum state. The quantum state is topological. So it's like you have like a conjugate. So if you have a -1, you have a +1. If you have two states, conjugate pairs, you get like if you get a minus plus, you have a plus minus, but they have different orders to it. So maybe plus minus in that operation is not polar to the one. So that's quasi. But the quasi system is really quantum state. The state is quasi if it flip up, if it spin up, spin up position and spin down based on how electrons spin. But if the spin is not really I'm giving you like a kind of invariant operation, because if I'm looking up or something, I'm looking down. This is down, so the other computer for the down instance based on the state. But I'm saying that the force of the 4-dimension width component XYZ is lost because it's spread across the other forces uniform distributed, so you don't have no effect on you or something that's obvious to take in consideration that you can act on. So the thing about the force quasi is just a topology state. So if I have like a 1 and a 1, 0 is 1, I have a 0 at the same time. If I have a 0, I have a 1. Based on binary option on an octal, there's some kind of two-way to resolve the state. And for two-way, you could do something. You have two operations, two encoding. Because the quantum system knows the states at the one time, at all the times, because it measures those two states at once. So that's the idea of the quasi system. The topology model must basically any 3D operations that leave the hidden axis, any 3D operation leaves a hidden axis on chain. because the hidden access is not the changing the force width equals 0. So you can never change the force width directly, because there's no direct way to interact with the force width, because you're not part of the force system, because you basically it's been separated, so you can tackle what you will need. But someone else knows that if you're in a 4D where you know the structure already, you have full access to it, because the structure is in your reality, your own view. You can observe the change. Maybe it's time, maybe it's something else that can give you a sparse model of a 3D world, or the width of that dimension, based on tensor system. The tensor is like very important to understand here, because the tensor can be if you have a 3D tensor, you have like 3 dimensions. You're looking at 1, 2, 3. You have like 9 dimensions to look at. 9 dimensions of input, 3 plus 3. 3D tensor. You have like a 3 inputs. So you have like a. So let me give some. Tensor is a topology model. So let me give an example. So 1D tensor. Basically, you have a 3D tensor. So you have like a matrix, a 3D matrix. That has x, y, z. Now, this XYZ is just one component. That's not topology, just one component. Now, you get the conjugate one, which is like the conjugate one is ZYX, if it's in ordering, so it's then you got the row conjugate and the column conjugate, the same thing. But the topology system for this XYZ component are based on the conjugate observation of operation. So therefore, you don't lose information. You just have a misaligned file system, because the conjugate, the lead axis is unchanged, because the identity is preserved. That's the function. For example, you have the tensor model here. So you have x, y, z in the matrix and in the vector. There has to be another if the tensor, the matrix A equals 5, 6, 9, and the matrix B A1 B equals 6, 2, 3, 6 to 3. You get AB. AB is the matrix. You get some CX equals CX, but this 6 can be if you have CX can be somewhat of other matrices as the same thing. CD is the same thing, but the row. Basically, if the AB is a column aligned, the working columns, the CD is the conjugate in rows. So they should flip with the input. So if I have 5, 6, 9 AB row, you get the conjugate of AB row will be 5, 6, 9. You get 9, 6, 5 for the A transpose, and you get the B transpose of 6 to 3. But there's some kind of basically we could just know there's a range boundary. So that's the A transpose B transpose based on the conjugate operation. But this is not good enough, because then you have 2 more states. So if I have 9, 6, 8, you get the opposite one. You get the minus 9, 6, 5. And then you get for A, because the all negative here, based on operation, because the flip of the operation is the conjugate model for the system, the scalar, and then you get 6. You get for 6, you get 6 minus 6 minus 2 and minus 3, because that's the J B conjugate, because the flips opposite, and then you get the row, go down to row and column aligned. So that's I'm giving you an example to go with. So I'm not done. So basically, transpose of the matrix. Let's say 2D matrix, 2 by 2 matrix. You have a 2 by 3 matrix, 2 4, which is a row or column. It doesn't really mean anything. So and you get the transpose. Basically, A is a matrix 2 4, 2 4. Now 2 4 is just one matrix row and column. It can be any way you want to put it. But the operation is uniform under transformation. So if I put the computer AT, which is at 4 2, that will be the flip of 2 4. Now 2 4 is just the first matrix, but when I get 4, the transpose matrix. Now the identity matrix is 4 times 2 is 8. 8 over 8. Now this identity matrix is just the start scalar state. This is called identity matrix. So A identity is like you get the identity, you get transpose, you flip the row column, the row to the column, and then you flip it. You just tilt it on its axis. So you rotate the whole matrix structure 90 degrees. So you move everything 1 to the right, and then basically you can start it. So if I have another one, I know someone will give you. So the A matrix 4 3 has the conjugate 3 4. But that conjugate doesn't mean it's like broken. This is transpose operation. So that's the transpose. I have to get the matrix it's same matrix, but it's a conjugate matrix. It's like it's the conjugate operation order matrix. So when it's reordered, you transpose it. If you transpose it again, you get the matrix. But the 8 8 is just the identity matrix. So if I have 8 in the one component and 1 in the component, I do rise over run 8 divided by 8, I get 1. Now the 1 is the identity signal. So this is a signal that is, oh yes, this matrix is identical. It's just the unit matrix. So this unit matrix can be for that frame of reference. Not from a frame reference to that thing you were measuring before. It's just this matrix. So the frame, the 8 or 8 just says, okay, this is my representation of my 1 unit. I've traveled from this 4 to scalar. So if I scale this way, this is my unit start minus 8 minus 8. And this minus 8 minus 8 can be used for any matrix if I base on some kind of set. So if I say I'm only working in units 10 units. So I have the maximum, the 10 in my core system. 10. So 10, 8 to 8 is the identity. A sub I, and then the A is a 4 or 2. The vector. Then you get the matrix that's relative to it. So if I pick a 2D matrix 6 3. B. Now B is 8 8. So if I want to use it, I can use the standard equation for this matrix to ensure that the system remembers it. So example, if I'm saying the center point is 0 0, then this matrix is 0. I know that some transformation obviously can invert this. So 8 8 is the unit. So that's just 1. So I can just say 4 times 8 times 8. That will be give me where my full reference from the center to the because I have to go through the identity matrix. 6 times 8 is what? 6 times 8. Let me try and work it. 8 times 6. 8 times 2 is 16. 32. 32. It's not working around. Basically, it's not working around. Basically, let me try and do it the way I did it. So if the basically I have to go to 6 3 is what I started. So I flip it. So I become 3 6. 3 6 I get 3 plus 3 6 3 times 3 is 18, and 6 times 3 and 3 times 6 is what? 18. 6 3. So I get the same 1. So there's some kind of relationship between 8 in their reference and 8 transpose and the B transpose 18 because just flip the numbers. Because that's the one. So basically I get the something called the lattice. Now the lattice in my view is the same thing, works on the intersection. So the lattice, like a geometry, works on the rotation, the transformation, the rotation, transformation, and the ecosystem. So rotate something, translate it, you move it x, y. You rotate something, by polar coordinate system, and then you enlarge something, you scale it up, and you get a reflection, which is like the system's conjugate pair on the other end of the axis on some kind of auxiliary line. So why this is important, guys? So we now define 8 8 as the starting point. 8 8. So I'll get back to you why I'm talking about, but you guys understand this first before you go any further. So 8 8 is the starting point of the new line. But 8 8 means what? 8 is my starting point. It's what we agree on as a protocol. So if I'm at some kind of lattice, some kind of point that is phenomenological, again A transpose 4 2. A equals 4 2. A transpose A sub T equals 2 4. This is just the thing, and you get this shear coordinate system 8 8. So 8 8. So this 8 8 is just the reference point for A to work with the B. Now B is 6 3, and the conjugate is B transport is B transport equals what? 3 6, and the 3 6 is what? 6 times 2 is 18. 3 times 6 is 18, and 6 times 2 is 18. And it's no. So basically, they share a lattice between the set space, an area based on A. So A, the A is identity A sub I, union B sub I will be some kind of intersection. So if I list the lattice at this should begin 8 8 x 8 8 2 less than equal to more than or equal to 8 8 and some kind of xy domain that share the projection of 18 to 18. So that's the only space you can share in the lattice model. That's the only place you can go to. But that's for union operation, disjoint operation, and intersection operation. That's what lattice is meant to do. So there's no blind spot in the system, because if there's a blind spot, the 4D force fails. Geometry boundaries. So I'll come back to this now. But 8 is one the identity they share. So anything based on the code system is a new frame of reference. What I'm saying to when they want to go together. So the thing I'm seeing here is 8. So if I have like if I want to add if I want the what's the style operation for the union. So 8 plus 18 is 28, 86, 66, 36. 36 is the union between 8 and 8, and then 8 and 8 is 36, 36. That's the maximum they share what they want to unify based on the range. Based on some kind of coin system, and then you get 18 minus 8, based on the intersection is just like any range between it. So the reason why this matters is because energy transfer via the system of entropy, which I come to via ODTS, OBINexus systems. So some kind of polynomial you can express with this formula. What's the formula? Negative boy couldn't decide whether to go negative boy couldn't decide whether to go to a radical party. Bean square bean square 4 over c. Bean square, he missed out 4 awesome chaps over 2 a.m. 2 a.m. That's like the polynomial formula. But this polynomial is for so if you solve this polynomial formula, you can get areas of parameters of the system, which I come back to now. So what do I mean by this? So the thing about this is based on entropy modeling. What I mean by that? So so you get the standard area formula, which is like the arc length. Now the arc length is a parameter of the length of the radius, something from center to radius, which is based on an observer model, and the sector is half of r squared theta, and then you get sector area. Then you get the entropy. Basically, it's a kinematics based on based on like some kind of graph structure. Let me try and give you that properly now. So let me draw it now. So let me try to do it properly, because I don't want to fuck it up, guys. So this is a one line here. 15 is 30. Now 15 of 15 is 30. Now 30 is there. Now 15 is 30. Now 15 is there. Therefore, you get epsilon or nil here, or 0, minus 180, minus 180, or plus 180. You get minus 180 epsilon or 0, nil. So what does this mean? So this is very important you guys understand this model I'm drawing. You can see it. I hope you can all see it here. No, you can see it. But the arc length is like if this is the center of the radius, the center of the circle, you get arc length. Oh no. So basically, if I'm traveling from point A and B, B are the spots. So let's continue an example. So the point 88, the point 42 is on one axis, one point axis. So let's call it point A. So point A dot x is ax, a sub x is 4, and a sub y xy is 42. And we work at the coefficients 2, 4. We're going to go that identity as 8, 8. Where it's gonna all meet in that intersection. And you get the other one, B, which is a 2D model of 18, 18. Now 1818 is like the intersection. So you get the 6, 3 and 6, 3, 6. So we get the 6, 3. 6, 3, we get the number 6, 3. 6, 3 is the x b axis, and you get the y 3, 6. Now this is 1818 a unit. So there's some kind of unity between this model, and that's some trying to implement here. So the lattice has to maintain the rotation of the structure without breaking the whole geometry. And why is it important for thermodynamics? So basically, you're gonna try to find this work this out with main Gaussian structures. So the sector area. So I got my photo from here. The arc length. So the theta, the arc length is a what? A length equals radius bound to this partial, this partial extent. Therefore, the area of pi is pi r squared. So basically, the pi r squared covers the area. The 2 pi covers it. Um, but what I'm saying is this. So basically, you got the model here to work with. Here. So the thing I'm saying is like the first law of thermodynamics, what's the first law of thermodynamics? Energy is system. The first one works, the second one works. The third one does not work. The first one states uh, energy is conserved, never conserved, and never destroyed. So you get it. So basically, you take 2 trips to get one. Say I'm trying to go to but me, all I have is energy to go there. I don't take stops, nothing. So in the system that's chaotic, energy is not used properly. It's kind of model diagram trying to do. So if I'm trying to go from point A once, but to B, I can do that. But I'm going to take the longest part. But longest part I can measure. It's a straight. The longest part I can measure is a straight. The shortest part is a straight line. But in this kind of entropy, it's when there's a lot of noise, you don't take it straight. You take 2 trips. Why? So basically, if you remember the Newton laws, you get a force equals mass moderation, and you get the force equals moderation. You get a net force equals 0, and you get net force equals 0, negative force equals negative force. For negative force. So the force equals mass concentration. What does it mean? So if I have something, a unit costs 1,000. So we get basically, I'm going and try to go to basically I'm going to define the speed properly. So for me to travel with the maximum force and get there once, based on the arc model, without going the longest with shortest part, which is the arc, the longest arc, radius along the perimeter of when not even the center, which is shortest part. The center is the shortest part. So you think about the arc now. I have to take the longest arc. So to take the longest arc, I need double it. So I need I need to take the perimeter 2 pi r. Now 2 pi r is basically 2 r is like if the radius is like like 1,000. A radius like let's say the radius is what 100 let's say 50 miles 50 radius is 50 miles r equals 50 2 pi is what, so 2 pi is like a 3.14 times 50 miles. Now 50 miles is fine, but 2 pi pi is a pi, so I have to do like 2 pi 3.14 times 2, which I try to work out now on my phone. It should just work out. So the idea is to conserve the energy without doing it. So I'm gonna give you the example because you're gonna conserve the energy in system. It doesn't matter what's an electric system or not. The system must remain solving the problem in real time without actually 2 pi. Where's 2 pi? 2 pi. 2 pi is what? 6.28318530. 1, 2, 3, 4, 5, 6, 7. 8, 6, 8, 6. So that's 2 pi. Times what? Times 50. But 50 is what? 50 times 50. This radius is 50. So that'll be 100. So I have to travel 100 up. Basically, if I'm measuring my time, my energy will be whatever the arc sector area I've traveled. That energy I'll have to go through. Because if I don't have energy for that area, I'm not going anywhere. Because the entropy, I'm bound to the entropy of the system. Because I need energy to go through the entropy to ensure there's no entropy. Because they are invariant. They're different jobs. So basically, if I have energy, there's noise. There's a lot of noise. So, but basically, entropy stabilizes stuff. Energy makes me good stuff, but the entropy is the thing I'm trying to not fight, because I'm trying to use to curve right, because I'm basically at the center of the circle. So the segment circle, the half circle is like the half segment is the name for that. Let's call it a half circle. I don't remember. It's like half circle. So that will be in this framework sector model. So the arc length is what length. The arc length is what the length of the arc, which is 180. 180, and that's r times r. So the r of this basically the arc length I'm trying to work out is the radius bound. So the radius of this arc length is r times r, 2 pi r. Now 2 pi r is just the parameter after travel. So if I'm at the arc length of 4 4 4 2 4 2. This 4 2 represents a coordinate system on the place I'm in. That's 4 2 is like the coordinate system, but as you get a polar form of its own, we call it polar systems. Correctly, because it's not a polar system. So the 4 2 has identity 8 8, and that's where the reference is. My reference is based mechanically on the identity. The between the epsilon states, two epsilon states that are both opposite. Polar opposite. How do I call Cartesian 2? So the 4 2 model is like, the polar coordinate system 4 times 2. So if I go 4 x, I go up once, but it's kind of polar opposition of this. So if I do we have to I'm to find out how to do calculus now. So 4x 2y 4x 2y is units, but it's a polar form of it. So this the polar will be out of 180. So if I'm going 4 up, am I going counterclockwise? I'm going counterclockwise. So I have to do times counterclockwise. So I have to do times 90 times 90. So basically, the way to calculate this calculate the polar system based on displacement. So 4 plus 4 up 2 2 s. So 2 side yes, that's 4. So 4 2 over 180. Now 180 is a travel. Then basically this is some kind of uniform. So that's 4 over 90, and then plus a 2 over 90, which will give me the split of the two polar systems. And then 4 over 90 will be what? 4 divided by 9. 4 divided by 9 is what? 4 divided by 9. 4 divided by 9. Uh, 4 divided by 9. Oh, sorry, guys. 4 divided by 90, 90. Basically, 4.5. So 4 times a half, because 90 is a half. So 5. Basically, if I do 4 divided by 90, that'll be polar wrong. So I'll do 4 times a half. I can do 4 times negative a half. Because if I'm going counterclockwise, moving counterclockwise, but that's counterclockwise. I'm not moving. Basically, that'll be 4 times negative a half. 4 times negative a half. Negative half of the 1 over 2. That'll be 4 times 0, negative 0.5 2. Basically 4 times 4 times dot 0 dot 5 will be 2. Basically, because I'm going counterclockwise, 4 times dot 4 times 4 times negative the 5 will be negative 2. Negative 2 in that framework, and then that will be negative 2 over 9 over 180 in my coordinate system. Some negative 2 degrees over 180. Same thing for the other one, because I'm going counterclockwise. And that'll be 2 the times negative negative a half, negative 2. 2 times negative 2 times negative 2 2 times 2 times negative 0.5, that would be negative 1 minus 2 to negative 1. My constant was just negative 1 over 180 180 degrees. So this coordinate system is the polar, what I'm going to be the polar equivalent of the Cartesian system, Cartesian 42, because there's the polar 1 degrees in degrees. So this negative 2 is over 180 degrees, and the other one for the system in the other one is 8 8. So its frame of reference is 8 8. 8 8 is the identity, and that's like this units of 1 1. What it thinks is this: I'm here, can find me in this location. So if I say 8 8, 8 8 will be 8 units up. So basically, you put on the table here. So we got 4 2. Basically, if I have 4 2, if someone give me, oh, say my location is 4 2, and then tell me, oh yes, my location is 4 2. I say yes, I know my location is 4 2. So but I give you where I think where I actually am, because you don't know this place enough for me. I'm actually at negative 2 degrees, negative 1. Based on the polar system. If you give me Cartesian. system. But you know, if I say one more thing, so that's basically I'm telling them I'm at 8 8. That's my 8 8 position. 8 degrees, 8 8. Basically, if I go through some kind of transpose, I get the unit 8 8 8 8. Now, if I have to do the same thing, it's going to go 8. So I do 8 times minus 5. 8 times minus 5. 8 times a half minus 5. 8 times minus 5. 8 times half. 8 times develop. 8 times half. Because I'm going counterclockwise. 8 times minus zero point 0.5 will be minus 0.4. Minus 0.4. So basically, we agree that you know we are at minus 0.4. The range minus 2 1. Minus 2 to 1 degrees to 4 minus 4 and minus 4 degrees going from B to A, you know, but not from A to B, from B to A. In reference to B first then A. This matrix is what I'm saying is very good to use. So the lattice of this will be any space, any area, any segment that minus 2 to minus 4 and minus 1 degrees to minus 4. You know, because you know that's the range boundaries. So any union will be in this degrees way in this degrees system here via the Cartesian one. You can check it. So the sector length of this is bound by the length. So if you don't know what I'm talking about, so to calculate sector length of this, so if I'm now traveling from this position called B to A and A to B, I have to do basically. Oh no, so that's A to B. No, so that's A. So that's A to B. A to B. Starting at basically A to B is going oh, this is going the wrong way. Basically I calculated it wrong, so this should be the flipped this should be times 5 because I'm going the wrong way, so I've lost the round. Basically I meant to go the right way because it's based on the union model, but that's what I'm saying to you, it's not as hard. I have to do it again. So I'm doing it again. So I'm at A, I'm going clockwise to B. So basically the energy you have to use like the as I cover the area under the curve, which is what the energy is. So again, let's try to do 3D. So we got 4 2, and the area of 4 2 the A is 4 2. Now AT is 2 4. No, we get 4 times 2 is 8. 2 times 4 that's identity. AI ATT 8 AI is 8 8. Now this 8 8 is very good to understand. That's the identity matrix. So the identity matrix is just a unit model. Now we share that A share all its operations. So this one of operation as unit, Lattice can use it. So that's it. And that's basically if you're going clockwise, the segment for this in Cartesian would be 8 8. The segment for, so if I'm looking for this theta times theta over 180, because the 180 degrees is just for the journey 180, so the theta times 80 times out of 1, because this is out of 1, so how much do I want to travel? If I travel 45 degrees, 45 degrees, that'll be 45 over 180 times the arc length, which is radius 2 pi r. So the 2 pi r is the area, the energy 2 pi r, the pi r squared. So the radius squared. So this is what I have to compute. So have that compute this 8 8, which equals system to radius. The radian. The radian is like the radian. Oh, basically this is half a radian. So this is half a radian. So to radian, I do 8 to radian. So 8 divided by 360 is what? 8 divided by 360 to radian. Pi radian times pi. So basically to radian, this would be 8 over 360 for the two coordinate system. But let's see how this holds true. So if I do this 4 divided by 360 is 0.1 times pi will be, so seriously, uh, 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 8 divided by 360 Am I going clockwise? No, 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 no. A to I'm going A to B, so I'm going counterclockwise. So that will be A divided by 360 times minus 80 times 180 times minus 180 because I'm going counterclockwise. So that'll be A divided by 360 times 180. And that'll be 4. So the 4 I'll be 4 if I'm meant to be in the lattice that I'm going to be. But in the frame of reference of the system, I'm literally at 4 divided by 2. 4 divided by 360 is the arc length. 4 divided by 360 times 4 divided by times so 180 times minus 180, because if I'm tidying them, I'm going counterclockwise times minus 180 times minus 180, and that will be minus 2. So minus 2, and then we'll do 2 minus 2, and we'll get y y minus 2, and I guess 2 minus 2 then we'll get 2 divided by 2 divided by 360, and that will be times 5 times 180 times no, sorry, times 2 divided by 360 times 180 times minus 180, and that will be minus 1. So 2 minus 1 minus 2 minus 1 backwards. So that's something I got here. Oh, so I did correct it right. I did get it right the first time. Oh, I did get it right. 2 degrees minus 1. So you see, I'm saying I did get it right. So that's what I'm saying. So that's condition is my frame of reference condition. But the same thing for the 6 and 3. 6 divided by 6 3. So we get the same thing. 6 divided by 3. 6 divided by 360 is the radian times what? Times what? 6 divided by 3 times 660. 6 divided by 360 is what? Times 1, 2. Times 180. Times 180, gotta be counterclockwise, that'll be 3. So if you're at 3, and then we get 3, 3 divided by 360. 3 divided by 360 times 180 is 1.5. 1.5. And that's 3, 1.5. 6 divided by 360 times 180. So they get times 180 is 0 times 180. Because I'm going to half. That's 3 to 1, 3, 5. So my coordinate system based on polar is minus 2 to 1, and and that is their one is 3 to 5. So I can define kind of the system here. Yeah. So this is I guess. So basically now the energy is now so basically that's my radius now to travel. Every unit based on the system of to get there enough time. So basically I'm trying to get up there in half the time because you have to double the force. So this unit force I get. So this force here, I have to consistently. So if I'm working on energy, I have to use the polar system. I have to be traveling 2 degrees every 2 degrees in 2 degrees every x coordinate, and that 2 degrees is the same as walking literally uh, working every year 42 units, 42 units based on 88 topology. Because if I'm working 40, if I'm at 40, if I'm at A start, I'm using the A start EF4 or 2. But I'm working like at the pace of a snail. But the identity is 88. So that chemical one 88 is there. To work on the maximum threshold, but I have to work at the space of the uh. So that'll be 2 4. That'll be identity flip. Oh, so that'll be fine. So basically, oh no, I can't go back. So basically, you got the standard formula for it, and that's the formula of the energy, which is what is holding the whole system back. Because energy has to dissipate correctly into the system. You can't have any high energy here and low energy here, because that means the system is naturally unstable, and that's what you try to do. Because the quantity state is stable, the sparse gradient flow, because the energy is not uniformly doing its job based on how it's tracked. So it's like ensuring the energy the area covers is sparse enough, and the room stays warm. There's no kind of override you need. Basically, energy density is like that's kind of lambda symbol. Energy density even as bulk energy equals zero. So density remains density zero remains finite over the area A, which is energy transfer over A, because energy density is the what is the calculated form, the optimal form. The density is gonna optimal for the density, but the entropy density is the same thing. That goes off final time. The energy density. So if the energy density is introduced with entropy, then you go something that's going to naturally be chaotic, and you cannot resolve the energy T via the area model. Give the area system, which is what the final thing. So basically, it's control of energy over the space of entropy density. So model ingredients. Observe Merlin and Hilbert space. Hilbert space. Okay, Hilbert space is lattice bound. So you get what you get lattice. So Hilbert space. What is Hilbert space? Hilbert space is a quantum space where all energy and matter coexist. Because it's just like the form, the bubble form. So you get like the Merlin space, because the bubble form. 3D work we can measure, see, control and measure. Control is based on lambda t. Is that gamma? No, lambda t of time coupled to the back. The bath is entropy. So the Merlin dimension, basically Merlin is like the show that basically Merlin tries to leave the soul from the stone, but Merlin is basically using magic. So Merlin cannot leave the soul in a 4 dimension, because that 4 dimension cannot access and it cannot measure. Therefore, since it cannot measure, it cannot access it and it cannot control it. The Hamiltonians block a diagonal or label it. So this is the Hamiltonian what's the Hamiltonian graph? Qubits Hamiltonian f in first in first out. Is it Eulerian? Okay, so Eulerian is based on which? So Eulerian is for Eulerian cycle. So you won't get Eulerian cycle during diagram the spot, but you get an Eulerian cycle. But Eulerian cycle measure the entropy of the area. So if you get the Hamiltonian, you're measuring the path, the nodes. So the nodes so you go to the path, but Hamiltonian path is based on depth first search, but Eulerian is based on breadth first search. But you can build anyhow based on Q. So you get basically Hamiltonian is based on a path, so that's based on Q. First answer, but Eulerian start manage edge based weights. So if you give it this weight, you have to have some way to resolve that weight based on kind of observer model, and that's what the Hamiltonian represents. So the lobes of the basically this symbol is like the thing. You can control and measure the hubs, but control the change in time. Lambda, the change of time, coupled to the balances, but the frozen population increase the accessible operators. Okay, so superlation rules, the forbidden transition. Mixing the hidden sectors requires for the physics forbidden or solution process. So basically, you're trying to degrade the system naturally, because you don't control your entropy. You don't control enough of what is being used at the time. So basically, the forbidden operation requires the bra, which is the conjugate bra, which is a bracket. So every bra has a cat. Every cat is a bra. Symmetry equals 0. So when the magnitude of m is the magnitude of m, the unit model Ga Gb gamma G gravity of alpha, what is the magnitude m of Gb approach to E, which is not m. The initial state is Ga, but the final state has to Gb. So the G has to be heat. It has to go uniform distribution of energy over the sector, arc sector, because the arc sector is what it is for. So if you're traveling 360, your arc will be, if I'm traveling like half the arc, that would be 90 degrees, and that is for basically after I can travel 45 degrees. If I'm going to 90 degrees, but the arc at 90 degrees is the same thing as saying that I'm traveling in segments. So I can model like so if I start at 180 if I start at 1, unit 1, the one, the point one, the point one, which is also zero, epsilon, depending on how well I move or not. The point one is a 1 degree movement. But that 1 degree movement is now I move 45 degrees. That's half. That could be half. That's half of 90. So I do half of 90 degrees, 45 degrees. Now 45 degrees divided by 90 times 2 pi r. Now 2 pi r gives me the perimeter. Pi r squared is what you gotta use to get the area you have traveled, and that will give you the dimensions you are in. How to continue? So you're talking the area. So for example, 45 degrees divided by 90 is what? 0.5. I've traveled halfway. Now 0.5 is half. Now I do times pi. Times pi will be what? Times 3. Times pi. That'll be the pi r pi will be 1.45. Oh no, pi divided by 2. So 0.5 basically 0.5 times 2, 1 times pi. That's 1 times pi. 2 pi. So basically 2 pi times 1. 2 pi times 1 times 1 times r. If my r is 50 miles, that'll be 100 pi I've traveled. But basically 100 pi for 45 degrees I've traveled. Because my pi is 50 miles. Then my reach is 50 miles. But that's 150 is half, so it's doubled. So it's in for the area. If I did so this is area. So if I covered an area of half, that'll be half of pi. That'll be 45 degrees. Energy I see. So 45 times 90, if I'm traveling 90 degrees, is basically 45 divided by 90, 2 pi r. So you can get pi r squared. So the pi will be 45. So if I'm saying the pi is what? The radius is 50, 100. So what is the pi? I don't know. The radius is 50. So the radius is 50. So if I do 50, 50. So if I do 50. Sorry guys, I have to end this video now because I think this video is getting too long. But let me do calculation now. 50 times r squared times 2. That'd be pi r squared. 100. Now I get 100, which is the square root, because it's r squared, so it's not 50 times 50, it's 50 squared. So 50 squared is 50 times 50 is what? That'll be 2,500. 2,500 represents the area of coverage. 2,500 squared. So that's basically the same thing for the radius I've put there. But r squared now I do times pi pi. And that'll be so basically if I'm traveling 100 centimeters, 100 miles, I've used the energy of 100 miles per whatever time frame I'm coming in, because I don't have to get the time involved. I don't have to put the time as an input because the time is sparse, because there's no time here. So if I travel 100 miles, I've walked like 7,000 times sorry, I've traveled 7,853 .981 to 981 6 981 6 3 or 6 64. So 98164. This is just 1 to 5 decimal places. So that's the ratio model, because the sparse modeling of the system. Because every 100 miles the energy has to come out of the system, but the energy has to be stabilized. So you go to literally just manage one state, and that is like having the having some kind of operation. Like if I use the energy, if I cap the energy to one half it's for the where I work. I do something else. I use some kind of other resource in the energy system to ensure the entropy is balanced and uniform in that system. Based on second order, because the time is not involved no more. It's just the energy dissipates. Because you have like a lack of control of it to get to that place, because the energy is the factor of time, but time doesn't it's not taking involved. Time is not needed. You can use time, but time is sparse, so you don't really have to optimize for time. You optimize for the derivatives of the time. They can calculate time in real time. And this I'm talking about So residue formula. Uh, Imagine system G topology. Basically, topology state is just two states. Has two states. So you have two states and two operations. That's what it is. Okay, guys. Thank you very much. Let me go now. Upload this video because if I don't upload this video now, I will never get it. So, residual entropy. Result is based on negative k. Basically, ijk are just x, y, z indexing. But the summation of the epsilon state is based on a bracket notation. But you have to ensure that there's no collapse at the symmetry. Ensure that the focal point of the ground form output can project the lens and ensure the superstructure remain grounded in its own experience. So basically, I'm saying the third law is not real because the energy doesn't slow the system down on its own weight. The system sustains itself if you put enough energy in it. But the energy you have to transcend. You have to have you have to double the energy. Basically, what I'm saying, you have to quadruple the energy to keep the system working. So if you're using like 2 units of energy, 1 to 2, and the energy has to go in area, work in areas, because energy is conserved. It's not linear. You optimize. You have to use the way to work it out using Hamiltonian energies and the graphs to get to the energy. Because you're watching the energy. You're basically observing the energy with the trace function and controlling it dynamically via partial derivation modeling. Which is what I'm saying is the next one, the polar coordinate system. The polynomial formula, which is a convolution of the states of times, the times and the when you basically times when you time something and you have another version of the time, that's a convolution. You time something, which is a timeser, and you get something that multiplier. That's convolution because the convolution series expects you to have the polynomial really set up. Which is what I'm saying. If the polynomial is not set up, the polynomial formula, a negative point, then the system will have two outputs. Will have two outputs. When one of those is nil, then the system has failed you. Now the system is not coherent enough to continue. Because if you have an x that is x1 that is 0, and y2 that is out of bounds like 32, when it's 1 to 30. If you get an x of 5 and you have a y of 32, then that y is out of bounds of the range. Then you have some kind of miscalculation and the system will start decoherent naturally based on the two solutions you're meant to yield in that field equation. The lattice is meant to join the solutions. This change is meant to keep the solutions that are not there traceable or not traceable. So you have solutions that actually ensure entropy is controlled, and you have something else the intersection state between the two energy for sustainable algebraic energy. Okay, thank you guys.